Hello everybody. Today we talk about how to design CPU. The CPU, in the previous video we talked about the instruction decoder. The instruction decoder is basically the state machine and if you have a associated cache, it has its own management. State machine. It's managed the cache, and it has memory interface, and actually there is the additional interrupt handling, and I'm going to talk about this one later specifically because most of CPU using very old architectures. A lot of new proposal coming up for the new architecture of interrupt handling. Now, these are mainly random logic. In the RISC, it's not organized in the microcode tables, which is the CISC CPU, and this is currently going on. There are many different improvements you can make in a CPU design in this area. Another one is called execution unit. And execution unit is the heart of the CPU. It's directly affect performance of CPU. What it means is how quick it can do certain job calculation, what type of calculation, add, multiply, divide, and also logical operation. Okay, now there are load and save, the moving data type of performance of CPU. This depends on how quick, how well it does, determine the CPU's performance. And now the MCU, those are the CPU that control the hardware, like robotics and appliance, IOs. Okay, execution unit is usually it's not the top priority in the CPU design. It has a lot of more other stuff comes in, but general purpose CPU, the performance of CPU become very important. Okay, so we focus on how to improve the performance here. We're talking about general purpose CPU. Now, traditionally, execution unit include register, right? And the register is like 32 bits times n register. Okay, so what is n? Okay, the traditionally it was limited because register costs a lot of gate numbers, because each flip-flop costs like about 10 gates. So if you have a 32-bit, it's already 320 gates multiplied by whatever n. So we try to limit n, but that's the old day. Nowadays hardware is very cheap. You can increase number of gate, so naturally you increase this n, then performance increase. Why? Because programmer can retain most of the data necessary in the register. They don't have to bring it back to memory. Once you bring the data back to memory, it's a slow process because memory is far away. It costs 10-20 clock cycle to access. So you want to avoid dealing with memory. And multiprocessor unit, the memory is shared by multiple CPUs, so you have a lot of complication there. So this is in programming term, it's local variable. Okay, once you bring it to memory, it's become global variable. Okay, so you can keep a lot of data you use immediately into the register, so naturally you increase the size of register. And there is some CPU architecture that this register is shared by multiple execution unit. So this become more complicated in programming wise, because you have to indicate which variable is doing calculation using which execution unit. So tendency is just forget it. Make it multi CPU. Each CPU contain its own register and execution unit. Okay, so you just simply put the full CPU. Then you don't have to share the register. Well, the sharing the register save the hardware, but there is a additional benefit for that, because the parameter is kind of shared. It's act like a shared cache. So each execution unit can share, but you bring that function nowadays to the common cache, and inside the CPU keep it clean, register and execution unit, so the program knows what to do. So each register contains the data and bring it to execution unit. Execution unit is usually indicated by this kind of ALU. You have a data A, data B, both coming from this register, and go back to typically same register, either A or B or brand new register C. Okay, so what does this ALU does is execution. So add, multiply, divide, and logical operation kind of stuff. So this is the design, execution unit design. It was boring subject a long time ago, but nowadays hardware is becoming cheap, and that means you can use more hardware to improve this. The obvious improvement is, so this execution unit after you put input data and get the result, how many clock cycles it takes, that's called latency. And if you reduce the latency, it's improved CPU performance. For sure, if A plus B takes 1 clock, then this result multiply by D, you have to wait only 1 clock to do this, right? But if A plus B takes 7 clocks, okay, you cannot do this until you finish this. So latency become important for dependency in calculation. Okay, now if calculation doesn't have a dependency, we have so-called pipelining. What pipelining is, clock 1, clock 2, 3, 4, and out. Now, when the data come in, it's do the execution, 1/4 of execution, and store in the register here. So ALU has a register, okay? Then you accept the next data for executing another 1/4 of job. While you do that, you send this to finish another 1/4 of job and store here in the register. You keep repeating, so it's like you get the data, execution 1, 2, 3, 4. If it's 6, latency is 6. Each segment of the execution unit does different calculation in pipeline fashion. If you do that, every clock you get the data out. So even latency is 6 this time. It's finished the job every clock. So this is automobile pipeline production, right? You put some the wheel here, car sheets here, and tire here, and car is done. So this is a pipeline operation, exactly same idea. So in order to do that, you need to have a register on each stage of the partial execution unit. But most of the supercomputer use this approach because every clock you get data, and most of the case in the scientific calculation you need independent calculation. For example, right, you have you get this value by and divide by kind of scientific formula. If you look at this area, it's all independent calculation. You can put it in pipeline, and this part you can put it in pipeline. At the end, you just execute one divide. Okay, making divide pipeline is a very difficult challenge, and even now the designer cannot do this right now. So I think only one done before is to get approximate divide value by table lookup. So one clock, look up the table and make it divide. So this is approximation. The speed is more important than the accuracy of calculation. That kind of case, you can achieve very high speed. Now, right now the pipeline is kind of built into the execution unit. This tend to be pipelining. But on top of that, we will do parallel CPU. Means you put this one here and put one next CPU and put this one next CPU and put one this next CPU and they execute together. Now the problem with this is you have to move this to this CPU. Moving time, data moving time become the issue. The execution can be faster than moving data, then there's no point of spreading into among the many CPU. So multi-CPU unit need special architecture. So it's like shared register. Register is shared, right? And which is faster than access. The access time is faster than shared cache kind of architecture. Now we talk about execution unit. We are going to explain how we design in a minute. It's execution unit happen to be very kind of developed, already fixed type of design for a long time until recently. This scientists in Russia, they try to make a computer not by binary but ternary. And the time the paper was put out, it was interesting, but nobody used it because it cost too much hardware, too many gates. But this day, gates are cheap. So recent CPU start using the ternary logic. So what a ternary logic compared with binary? Binary is 0, 1. Ternary is 0, 1, 2. But this form of ternary is not easy to use. What we look at, which works very well in a ternary design, is negative 1, 1, 0, and 1. Okay. So you have a 3-state. In order to have a 3-state, you need 2 bits. That's where the hardware cost, right? So negative 1, 0, 1, and 2-bit, bit plus bit minus. Negative 1 is 0, 1, 0, 0, or 1, 0. So there is a state 1, 1 not used at all. And this is important because every design, logic design, is done so that it's never produced this state. Then in the next logic design, you can optimize, assuming the incoming bit never go 1, 1. Okay, so eliminating this case, actually it's look like it's wasting, but it save a lot in logic design from my experience. If you start using this ternary logic, this is always very important. You have to make sure no matter what, the logic never produce this state, this undefined state. So you can count on it when you bring it to the next logic, those data, you can exclude this. By assuming this never happened, logic equation can be simplified quite a lot. So how you convert binary to ternary? It's easy, right? Binary is 0, 1, so it's just responding 0, 1. And initially conversion, -1 never happened, right? Okay, how about ternary? You still need a binary because it's the main memory, everything is binary. So you have to consider conversion ternary to binary. Well, you have actually two numbers that contain 0 and 1, and V contains 0 and -1. It's very easy to separate out, right? For example, one ternary number is like 0, 1, -1, 0, 0, -1, 1. So you have 0, 1, 0, 0, 0, 0, 1. B is 0, 0, 1, 0, 0, 1, 0. Okay, so you can easily separate into two binary number. Okay, but you want final binary number, so it's going to be A minus B, right? So you have to do adding or subtraction calculation to convert to the binary again. But remember here, this calculation is not a general CPU. The CPU with the condition that A, look at this, bit and B bit never be 1 at the same time. So this CPU is much more simple. That's gonna be the conversion to one binary number. Okay, so after you do this conversion can be done on the way to memory, like if you need to go to memory, and you have to set the boundary of how much is the ternary number and how much is the binary number. For example, here's a register and you have ALU, and we use ternary to reduce latency and calculation speed, so it's ultimately increase clock speed. Okay, now you have instruction decoder controlling execution unit and cache before you go to memory. So how much of this CPU can be ternary logic? Everything ternary? You don't have to do ternary on the instruction decoder because it's mainly random logic and it's not time critical usually. This is a guy time critical for performance, right? And the cache, you want to make it ternary? Well, maybe not. So when the data is moved to cache, load and save in and out, we put here converter ternary to binary, single clock, right? Because from this output you have to move to data register in the instruction decoder. So you can insert here, then it can be binary. And when you bring it here to the register, this automatically binary to ternary conversion, right? Because binary to ternary conversion is automatic. You don't have to do anything. You just copy into one side of ternary. If you have a B plus, B minus, you just copy into the B plus. That's, you copy binary number into B plus, it's going to be ternary number already, and the B minus register is 0. And only when you bring it back to binary word, this is a binary word, and this is a ternary word, you need to do conversion. But this conversion can be done simple. So here's your homework. This is gonna be 2 details in the YouTube video. The convert ternary number to binary number with the fact that B plus and B minus, this never happen. Both are 1. It's never happen. Okay. So this is your homework. Okay. You have to be able to do that. Okay. So then traditionally, how the number was added, right? A plus B. Say 32-bit numbers, and number format is, 2's complement, and 2's complement means A minus B. How do you perform this? A minus B. It can be this, right? And negative B is what? It's going to be complement, B complement plus 1, right? Okay, so it's addition again, just you need a 1. So you have A and B coming in, and you need to have this C input. If negative, you take a complement of B and add 1. That's perform A minus B, right? And other logical operation, we will get to that later, but this is what it is. So and the binary number has an issue, just like the regular number. For example, when you add 2, 3, 7, 1, and 7, 2, 2, 9. So what's happened here? You have 1 carry, 1 carry again, 1 carry again, right? So you have a carry hopping here, and binary, the same thing happened, right? And 1, 0, 0, 1, 0, and 1, and C 1 coming in. So this gonna create carry. So although A and B and A plus B is simple, it's an exclusive OR, right? 0 0 0 1 1 0 1 1. So exclusive OR, this is going to be 0 0 0 0 1 1 0. This exclusive OR, and you have a C out, carry out. In this case, 1 0 0. But if you have a carry in, then you have to expand this table. So whatever the table is, the conventional ALU design is A plus B part is easy, just exclusive OR. But you have to handle the carry. And if you carry hop around 32 times, this is not a good news, because you have a 32 gates to go through. Whatever the delay time of the gate times 32 is going to be the carry. And until you see carry come or not, you have to check this one. The execution is not complete. You can have A, B here, but have a carry. So that's going to be the critical timing critical calculation. How do you get the carry? So we had the clever way called carry look ahead. So basically, you think about data, check the 4-bit, right? And the carry may come in. What kind of case you have carry out? You think about this, right? So you add this one, it's going to be A exclusive of B. The A exclusive B, this is 1 1 1 1 and carry. This is going to cause a carry out, right? Or this gonna be 0 1 1 1 1, then carry out. That means A and B both are high, right? So naturally you see AND gate and the carry in is one case, and 1 2 3 and A and B is going to be another case. So you have 4 cases all OR'd together. Then you know it's going to be carry out. So this is called carry out, carry look ahead. So what you do is 32-bit, you divide into 8 of them, 4-bit each. So you know carry out from here to here for each unit. Then you apply this to the same logic, carry look ahead, in the second stage and the third stage. So you know carry out. Okay, so each stage carry out, say this is second stage, this has a carry out, go back. So in this logical design, timing critical path is going to be A and B come in, and the first stage carry out, second stage carry out, third stage carry out, go back. So at least it's going to reduce the critical path by half or less. Okay, you have to work out this detailed logic design. I'm not gonna design ALU here. I think you should try this. So this was a design used for ALU for a long time. This was the best, smartest way to speed up the addition of A and B. Now, when you change to ternary logic, magic happen. Carry, propagate. This hopping carry is called carry propagate. This disappear. It's never happened. So here's a second homework. Prove this. And this is logic design, but it's like a math problem. If you use ternary logic, means A plus and A minus come in, and B plus and B minus come in, and you execute A plus B, right? So you design a logic, a addition, you perform addition using ternary logic. And what's happened, this ternary logic, if you design right, carry propagate never happen. So it's completely removed the carry propagate. The gate delay become like maybe 4 gates. Instead of carry, look at it, still has a 16 gate delay. So dramatic improvement in the addition. Okay, this is your homework number 2. You have to design. I'm not gonna design here. The YouTube video is going to be like 2-3 hours long. Okay, now how about multiplication? What was the best, smartest way to do multiplication before ternary logic? Okay, you have multiplication here, right? A times B, and B is written this way, column. And you multiply you have to shift the digit, just like multiplication 3 4 4 times 2 5 2. So you multiply 6 8 8, and you multiply 15 20 20, and you multiply here 6 8 8, and you add up. Same thing you do binary, right? So you have, if 32 bit times 2, 32, this many number to add in each digit position, because result is 64 bit, right? This result is 6 digit. Now you add this, each one, it takes what, 16 add plus 8 add plus 4 add plus so and so. Is that right? This 32-bit. Your number of add is going to be so and so. So number of add you can calculate using this equation. So this is if you add row by row, that's gonna be this. Now there is a smart person who invented Wallace tree. Wallace. What he does is you suppose this is a sheet of paper. You put the sheet of paper like this, right? And you take this one to do the add. You take this one to do the add. You take this one to do the add. So like a sheet of paper on the top, you create a lot of add below to perform. And add, this is by binary, is added together. Okay, so if you do that, this length is going to be log n. It's much better than this, right? So what's happened? Ternary logic, you apply the same. You have 32 by 32 component to be added, right? But they are ternary number. Then addition, this binary number, each even number of add reduced, each add costs you like a 16 clock gates. Ternary logic is 2 gates, and you add all together. So it's like compare with this one, it's going to be this much calculation to get the final 64-bit in ternary logic. Okay, so you reduce the calculation time significantly using same Wallace tree, but number system is ternary logic, not the binary. Okay, so this detail, again, homework 3, you work it out. See, this is gonna take at least 1 week for you to design this, but once it's done, you feel very satisfied because you reduce calculation time so much using ternary logic. The result is ternary number, so 2 number in 64-bit, and this is the ternary number. Okay, so divide is a tough one, and I don't get into divide here. This is beyond the scope of this YouTube videos, but any company who want me to give some idea on how to improve the divide, I can be a consultant. This is like PhD guy work for me to create some improvement. It's not sufficient, but it's significantly improved. You can, if you want, you can do divide the pipeline fashion too. But generally speaking, you try to avoid the divide in any calculation. Like AI, you don't need a divide. You need only add and multiply. And divide is only for scientific calculation. In scientific calculation, you manipulate the formula and try to avoid the divide. Well, reciprocal number is a divide. Sometimes you need a reciprocal number, so you have to work on reciprocal number. That's a hint for dealing with divide. Okay, so remaining the shift and logical and or of ternary logic is very simple, right? And this is gonna be your homework. Homework 4, logical operation and the shift of ternary logic. Okay, I'm a little bit tired today, so if you think this is very useful video, please subscribe, and so you get the next videos notification. And also you can go back and should go through all the video so far published. I think it's deal with all the electronics, not only CPU. Okay.